that should be sufficient to set up the problem. Any question about it? You guys remember it? Yes, maybe? Am I speaking just to nobody? Apparently nobody. There's a current through each one of the spokes, right, due to the potential difference. Based on Kirchhoff's laws, 1/6 of the current goes across each spoke to the outer edge because the current has to split into 6 ways. It's a parallel circuit. Now, I don't care at all about the number part of this. The question was asked about the torque. And although I won't go into the question so much, it should have been brought up by more than one of you. But maybe you didn't get this far. I don't know. I should care more. This one spoke is experiencing a force, right? The current is constant. The magnetic field is constant. The size of that force would be ILB, sine the angle between the length of the wire and the direction of the magnetic field, which by all accounts is 90 degrees for every one of the spokes, right? Because we're talking about a current that travels radially along the spoke and a magnetic field into the board. Now, look, I can say those words, but it's easy to tell those of you who are actually paying attention and those of you who are just giving it like the, I'm watching the board thing. Because those of you who are trying to figure it out have one of these going on. They're trying to understand where the angles are and what's supposed to be working out together. If you're not doing that, I'm just going to assume you don't know why it's 90 degrees. But you should understand that this is a constant everywhere along the wire. I'm saying that L, though, is this length. And see, that should have been obvious without me drawing it in. That's why I get concerned when I see you guys like filling it in now. You should be able to. Now, outside of all the electronic parts of this, because there are electronic parts of this, there's the fact that the current is actually related to the potential difference that was applied, divided by, the resistance of the system. There is the fact that the current is then divided by 6 because there are 6 wires. These are all the electronic parts of the circuit. I'm not even talking about that. You were asked for the torque on the system. I'd argue you guys can't find the torque on a single wire. Have you tried? If so, what did you do? Because I'm very interested, since torque is R cross F. What was R? Put your hands down. Because unless you integrated, you did it wrong. Plain and simple. Because if you just assumed something like it happens at the midpoint, why? Why would you make that assumption? That's a terrible assumption to make. Or to just look it up and verify, that makes sense, it's at the midpoint. So you put your hands up here and say, it's right at the middle. Why? I noticed that the 2 hands that went up are both calculus BC students. No, you're not? All right, well, calculus students. Right? That part has to be true. Why do we assume it happens at the middle? There's no reason for that. I think you should prove why it happens at the middle. The answer key says middle. And as far as I'm concerned, I'm afraid that might be the only explanation. It's not because it's the center of mass. That wouldn't make any sense. Mass of the wire was not even suggested here. And the only time so far in the past that we've concentrated a force at the center of mass is when we're dealing with gravity. And gravity acting on an object causes a torque, which would not have been brought up in this class. So why the middle? Now you can prove it. Did anybody attempt to prove it? A little sadness. But, of course, I'm not sure anybody finished the problem either. So, there's that. I'll take the blame for that. Didn't press it on you. Got busy with other stuff. Moved on with curriculum. Do you know how to prove it? See, I'd say that without me, I did something. What I said to myself was, because I was asked this question and I didn't have a prepared answer, I took a look at one wire and recognized that, well, we know that there's current passing through the wire equal to I. And we know that the entire wire is surrounded by a magnetic field that is uniform. If it was just the wire, we would say that the force is equal to IL times B. That's what we would have said. And in class, I even made this clear that, okay, that produces a force that is spread out everywhere along the wire. Make sense? The problem with that statement is the wire is affixed at one end and is required to pivot. So some forces have a larger effect on the torque than other forces. Right? So it seems to me the best way to deal with that would be to break this up into small segments and add up the net torque on the wire. Right? Because we know net torque equals, I alpha. But net torque is just an integral. In the case of this problem, I'd argue that this integral is F dot dr. Not dot, F cross dr. Where dr represents a small piece of the wire some distance away from the pivot point. I have to work in that distance somehow based on the force. I think I can. Because I think, to be honest with you, that when I look to do this, I think I'm going to take my force and say that it might, instead of being F dot dr, is R dot df. R points to a piece of the wire. There's a piece of wire right here that is experiencing a force. How much force? Well, df equals I, how much wire? dr amount of wire. How big a force is it on each piece of the wire? I'm just taking L and breaking it up into small pieces, which I'll call dr because they're along the direction of R. Now, what that does for me is it provides me with a way to add up all of the individual pieces of force that act every distance away from the pivot point. And so I'm going to start at 0 and go all the way to the end of the wire, and I'm going to say that that is my net torque. All right, it's a sum. And an integral is a sum. So let's do a little bit of substitution. Substitution. All right. I'll have 0 to L, R, and I'm going to do I dr times B. Now, I left out the cross product, but I don't think I have to really serve that to you guys too much, do I? The force has to be perpendicular to the wire and to the magnetic field, which forces it to be 90 degrees between DF and R. So it's 90 degrees for every piece of the wire, right? So I get that my net torque is going to be that. Well, the current is a constant everywhere in the wire, and the magnetic field is a constant everywhere in the wire. So I can pull out I and B, and I have the integral from 0 to L of R dr. Let's continue over here, perhaps. And I don't think I have to do a lot here. The integral of r with respect to r is 1/2 r squared. So this will just be IB times 1/2 L squared. We good there? So let's reorganize this. So I get 1/2 L out front and ILB right in the back. Now, I think I've proven that we can treat the torque arm as acting in the middle of the wire, and that our force is still related to ILB based on the whole wire. Right? But what we've also done is we've proven that in a situation where perhaps the current isn't constant, maybe depends on where you are in the wire, or if the magnetic field isn't constant, maybe it is non-uniform and you want to figure out the net torque, you now have a way to do it. Not that that's going to be on the exam, but there's no reason to believe it couldn't be. There's nothing here that's all outlandish, is there? So, to prove it to me that you're paying attention, what if on the test tomorrow, instead of having a spoked wheel, I had let me see if I can draw this correctly. Probably won't be able to, but I'll do my best. I had a solid metal disc. You see, because I think sometimes you pay attention, and I think sometimes you really don't. Now, it might not make any difference for your test score anyways, but this is in most textbooks somewhere, so you should be able to look this one up too. There. If I put this metal disc under this circumstance, where there's a magnetic field everywhere around the disc, would it spin? It would. It will. Sure, why won't it? Same reason as before. The problem is that the current density is changing from the center of the disk to the outer edge of the disk. So the force on any one point of this disk won't be the same. Each concentric ring would be experiencing a different force as you get out towards the edge. You could sum it up and find the torque, though. You sure could. Because the inside to the outside edge of this disk have to be at the same change in potential that's being applied. And yes, a current would go through this. This would work just fine. This is a motor. It's not a particularly efficient motor, but it is a motor. And if you wanted to find the torque, you would have to integrate the force as it changes along the length of one point. Just pick any path from the inside to the outside edge, and you can construct an expression for the current based on R. Now, I'm not putting this on tomorrow's test. What I'm saying to you is if you're paying attention, you'd understand why this is not a terribly unreasonable expectation. But I wouldn't, because this would blow you out of the water. This is a tough question. Yes, sir?
What direction would that be spinning?
Oh, why would I want to tell you that? But it would be the exact same direction as if it was a spoke. I mean, remember, the only thing that's different about this is that I haven't cut out spokes, right? In the other wheel, we just had spokes cut out of it. Although you kind of think of those wires as receiving the force, but remember, what's receiving the force are the individual charged particles inside the disk. So, It's an interesting thought experiment. You should try it. And no, I'm not honoring any questions on it. You try a little work on it first, and then bring me your questions, because I don't want you to just throw some crap at me right now. So just put them down. I'm not trying to be. Yesterday we were talking about the torque on a motor, and I was unable to draw it in such a way that I thought would be helpful. So for those of you who were here, you can tell me which number this was, because I don't remember which number it was. But for those of you who weren't here, we were trying to go through the homework questions, and a whole bunch of them have to do with a square loop of wire. So I want to speak to that problem, and I want to speak to it as clearly as I can. So it starts with something like this, and I want to be able to draw this in a manner that is capable of helping us understand what's happening, which I could not do yesterday. So give me just a second. As good as I'm going to get. So I want to make our magnetic field downwards, like so. And I want to consider 3 situations. And I may not be able to get all 3 of them on the screen at once, but I'm going to do my best. So I may have to do some sliding over to do it. So let's start with the loop, and we'll go with the square loop. Perfectly horizontal. Like so. I don't know if that's perfectly horizontal. Let's see, Mr. Shelton, can you do better? Probably not. Remember, just keep in mind, you have it on record that you shut down a student and wouldn't answer a question. Probably be used against you. And let's rotate it a small amount. Again, trying to carefully draw this. And then finally, all right. So it's spinning. I have created 3 snapshots in its motion. Everybody can imagine those 3 snapshots? So snapshot number 1 represents when we have maximum flux. Snapshot number 2, we are reducing the flux. Snapshot number 3, we have no flux. So although the system is spinning, and I'm afraid that when I write this on the board, I have lost a large number of you. But this represents, say, time equals 0. This represents time 1, and this represents time 2. It is spinning. Everybody okay? So this theta is theta equals 0. This theta is somewhere in the middle. It's not any particular angle, but it's not 0, and it's not pi over 2. Everybody okay with that? It's spinning, though, so every period, it goes back through this process and comes back to 0, something in the middle, and pi over 2, and then continues. Everybody follow along with that? Okay. There's a lot I need you to do here. So the first thing I want you to do is, I think I've done a decent job of drawing this in a three-dimensional manner. Would you agree? All right, so can you draw arrows to indicate the direction of the current in the middle picture? You'd have to use Lenz's law to do so. Is the flux increasing or decreasing? Decreasing. Therefore, the current has to be in a direction that will try and reinforce the magnetic field that is there. So I want a magnetic field that is downward through the loop, which is going to require a current this way in that wire because it's closer to us, and that way in the wire on the other side because it's further away. And by doing that little loop thing and thinking in my three-dimensional head, that's got to be causing a magnetic field through the loop in this direction to try and increase the flux. Yes, Caden.
Is it rotating right or left? Counterclockwise or clockwise?
Is it rotating right or left? Counterclockwise or clockwise?
Clockwise.
I think it's obvious, but obviously it's not. So it is rotating like this.
Thank you. It's very nice animation.
Thanks. I've worked on it all night long. I don't know how you can't tell that, but okay. But it's okay, because three-dimensional on a two-dimensional drawing is tough. But I think it's doing this. Can we all be okay with that? Oliver must stand for it. It's okay. So we're all good so far? We're all following along okay, right? Now, I can do this because I remember things. I would like it if you could remember things. But the flux here has to be B times A times the cosine of 0 degrees. A is the area of the loop. B is the magnetic field. Any question about it? You should know that that's true, especially because when we did this yesterday, A was just S squared. But A just represents the area of the loop. It could be a circular loop. It wouldn't matter. And the flux here is going to be B times A times the cosine of whatever theta is. It doesn't matter. It's something between 0 and pi over 2. And the flux here is going to be B times A times the cosine of pi over 2, which you all know must be 0. Well, I hope you all know that, because the cosine of pi over 2 is 0. But you could look at the picture. There's no flux under this circumstance. The magnetic field lines do not go through the loop. Are we all good? Here's where it gets squirrely. Inside there, the real flux is B, A, cosine omega t. Right? It's constantly spinning. I could put the little animation back up there if you need it. But it's constantly spinning, and omega represents how fast it is spinning. We have chosen 3 snapshots, right? But it's constantly spinning. So we have picked 3 separate times to look at it. But it's doing this over and over and over again. I'm looking at just 1/4 of the spin. So 1/4 of a period being the time it takes to go all the way around once. Everybody okay so far? I need you to buy in. If you're not following now, you're not going to follow the rest. Are we good? So nobody's going to come up to tutoring tonight and say, I didn't get that thing you did in class today. And then I will be unable to answer your question. Because from my house, you'll hear the scream. So you're all good. I'm being careful. Well, the derivative of this has to be the EMF. And therefore also the current. Right? It's a short jog from here to how much current must be in the loop. And you take the derivative with respect to time. So barring direction, because we handled direction already, the EMF has to be B, A, omega, sine omega t. Knocking out all of the positives and negatives. I'm not even putting the n in there because it's one loop. I take the derivative. B and A are constants. The derivative of cosine is negative sine. Get rid of the negative sign. And then because of the chain rule, I have to take the derivative of omega t with respect to t, and that gives me the omega. I shouldn't have to explain all of that. I did. So you should all be good. And since dividing this by the resistance of the loop gives me the current, I should be able to say that the current here equals B A omega over R sine something. And here is B A omega over R sine something. And I equals B A omega over R sine something. I'm writing that in all three circumstances because I want you to think about something that I'm afraid you're not thinking of, and I want you to. I want you to understand things and why math has to work the way it does. Maximum current occurs when the flux is changing the fastest. But we know when that has to be now. Pi over 2 produces a sine of 1. This has to be when the current is max. We get maximum current at this instant, the instant the motor's top centered. Not motor, the instant the generator's top centered. But current here has to be 0, the point at where I have maximum flux. Now, if you're thinking about it for just a minute, imagine looking down on this. Okay, you're looking down on it. So you're seeing the square of wire collapse to nothing and then open back up. And collapse to nothing and open back up. And collapse to nothing and open back up, right? That's what you're seeing from the square of wire opening and closing. It's spinning, but you're just seeing the two sides of the wire come together, because now that's it's flat, and open back up. The flux is the change in area. When it's big, the change in area isn't changing very much on the outside edge of that function. It changes the most when it goes right through the center. That's when the area is changing the fastest. So I get maximum current over here. I get no current here. Sheldon, what's the point? Torque. I asked you to think about the torque. Torque occurs because nature wants this to stop moving. Right? You can't get something for nothing. We can't just generate a current without that energy coming from somewhere. There has to be a force on this system to keep it moving or it will stop. However, there can't be any torque here because there's definitely no force here because there's no current here. Remember, we can't get away from the fact that current is ILB. Or more importantly, ILB sine some different angle. Be careful. The theta isn't the same angle as what we will use for torque. Well, where the current is max, I hope you notice that we have a problem with calculating torque. There'll be a force, sure, but it doesn't cause a torque, does it? Right-hand rule. If you look at the top and bottom of this picture, the current is a maximum and it's going into the board here and coming out of the board here. Using my right-hand rule, right? I put my ILB. So current there, magnetic field there. I've got my thumb pointing to the right. There must be a force here. and I come out of the board, magnetic field down. It's got to be a force here. And they're all perfectly 90 degrees, so it's maximum torque. Over here, try the same thing. This wire, current's going that way. This wire, current's going that way. Get a force this way and a force this way. But it's smaller because of the angle. Right? The angle's not 90 degrees. And the current is not at a max. But you'll notice that these two scenarios suggest that there's going to be a torque produced that's going to attempt to stop the motor from turning. I'm sorry, I keep saying motor. Stop the generator from turning. Torque is building here. And you should be able to come up with an expression for this torque based on the angle. No calculus involved. You have an expression for the current if we just drop the angle in there. The force is ILB. And based on the fact that this has a side length of S, the torque arm is 1/2 S times 2 because there's two forces. But over here, current is max, angle is max, suggesting here torque is maxed. So if you're trying to spin this, you would have to provide a counter torque in the direction that you want it to spin. And clearly, it wouldn't be a consistent torque. If you provided a consistent torque, our object will be not traveling at a constant speed. If you want your object to travel at a constant speed, you would have to provide a torque that also has sine or cosine wave properties. You must put away your books, and I'm sure you're happy about that.